Um, Hello, good evening, everyone. Today, this is the we have postponed our TA that is scheduled for the 17th September, and now we are doing today this one. Okay, so today in this assignment, assignment number 7, we will discuss a few questions about the polymer that we have discussed in the lecture 31, 32, and remaining we will discuss on the XRD pattern, all that here. Okay. So we will discuss one by one the all the question that is given in the assignment. We will discuss one by one, and if somebody has, if anyone have any doubt, then you can raise your hand or you can type in your the chat box so that we can so that I can see and we discuss that problem one. Okay. So let's start the assignment. Move to the question number 1. So in the question number 1. What is the repeating units in Lino are linked together by? So what is the repeating unit in the Lino? So basically, we all know that we nylon nylon is a polymer, and if it is a polymer, so it has a repeating units. So what will be the repeating unit? Is it the aldehyde group or the it's just the aldehyde group, amide group, hydroxyl group, amine group? So which of the following is the repeating unit in the lino? Basically, first we should know about what is the lino structure of. If I draw, the lino should be the this is if this is CH2 that C that is linked with the nitrogen, then another is the CH2, then CH2, 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 and the CH2, and this is propagating, and another layer, one sheet of layer. If this is the CH2, this is C. If this is N, let me make it, this is N, then it is again CH2, something CH2, and this like this. This C O bond, and there is the hydrogen bonding that is existed between the O and H. Here the hydrogen bonding with this thing. If I say H and then this bond, so it is something like this. So this is my the nylon structure. So what is the repeating unit in the nylon? That is, if you know that, what is the, if I'm saying this is the polyamide structure. In polyamide structure, what we have, this is C double bond O N H. This is, and you can see this, and this will repeat. This the whole complete unit will repeat here. If this is C, I mean the CH2, then C. If it is the it is N here, or the C, then it will be this C N. there will be bonding here also, H. Then this is like the repeating unit one. So if I see in the polyamide, so the polyamide structure is having the this C double bond O, this N, A, and with this is connected with the, this is my polyamide group. Okay, and you can see here, this is also my, this is existing it here. This group is existing in your nylon structure. So this is also the polyamide group. And this is have, what is this here? This is the hydrogen bonding in the nylon that we have shown here. This is the hydrogen. So we can see from this the nylon structure, we have the polyamide group in the nylon 1, nylon 6. So the repeating unit will be of the which group belongs to which group will be belong to the amide group. Okay, so B will be the correct answer. If I write the monomer in the short form, then your monomer will be the NHCH2. This is 6 time, then NHCO CH2 4, and this is again CO. So this is the monomer unit, or the this is the monomer for the nylon, or you can say this is the repeating unit for the nylon, and this is of, this belongs to the polyamide group. Okay, so the repeating monomer belongs to the amide group, and you can see from here also this structure is also shown. This is also, and this is also a nylon structure, and here you can see that this is the hydrogen bonding existing between this oxygen and the hydrogen one, and this is the polyamide group. Again you can see here, this is a polyamide group. So the this monomer unit is having the polyamide group. Okay, this is about the nylon. This is the structure of the nylon, and this is the monomer unit of the nylon one. Okay, let's move to the question number second. In the question number second, what we have, the vulcanization of the natural rubber takes place by its treatment with. Okay, we know that we whatever we use in the rubber, that tire or in the something else, that is not the natural rubber. Natural rubber is something of I mean the of liquid form, more of liquid like structure, but whatever we are having, that is due to of vulcanization. So basically what happened in the vulcanization, we vulcanization is basically we heat this natural rubber with the with sulfur, or we will add this sulfur in the natural rubber, so that we get the cross linking, and because of this cross linking we get the hardness and all over the hardness, flexibility. This depend upon the how much cross linking in the natural rubber. So vulcanization of the natural takes place by the with the treatment of the sulfur. If you see here, this if the natural rubber, if I talk about the natural rubber, and then we have the elastomer according to, I'm just talking about the elasticity order, and then we have the ebonite one. And in the natural rubber, there is no cross linking. I mean, there is no sulfur there. We don't have any sulfur, so there is no cross linking. No cross linking in the natural. In elastomer, we have the slight, the slight cross linking, and ebonite, we have the substantial cross linking. Okay, with the addition of the sulfur, or the cross linking will increase, and we will move to the natural rubber, to the elastomer, and then the ebonite one. This natural rubber is used for the, this is having the form of the liquid like structure, and this is having the elastomer is the basic, the elastic thing that we use, like the elastic thing like the rubber one, and the ebonite is belong to the, these are the hard and the brittle one, because we have done the vulcanization, yeah, this vulcanization so much that the cross linkage is to become a large in the quantity, and we have the now the my material, this liquid like structure become the hard and the brittle one. With cross linking, the your hardness will going to increase with the cross linking. Okay, this is a, if I say what will be the natural labor, how the vulcanization happen in this one. So if I see, we have natural labor like this way. If we have C H double bond C H, this one bond C, one is methyl is having this one with double bond C H, the H1, and we have the another unit of this thing. We have again C, and we have the sulfur sitting it here again. C H H C, or we can say H. Okay, this is double bonded C S3 C H and H. What happened? And this is my basically the isopropene molecule. Natural rubber is my isopropene molecule, and we do the vulcanization with the sulfur element. So after what happened, this one, this convert to the my, well, after vulcanization, this will become the C H, yeah, C H, this cross link with the sulfur one, and again C H double bond here, yeah, this H double bond CH3 single bond C CH3 S CH, there is one H, yep, there is one already there. So one, two, three, no. Okay, so this sulfur atom that is not earlier existing in your isopropene molecule, now with this my this double bond converted to into the single bond, and this sulfur is attached to my this chain of molecule, and with the this one. So this have reduced the flexibility. I mean so that's why we once when we do the cross linking, so this hardness will increases with the time as we do the vulcanization one. So there is one group S, also there is addition of S here that link the both the chains here, both the sheet or both these molecules, and also propane molecules, and also here this sulfur also has linked the both the, so the cross linking between the different isopropane molecules, isopropane molecule is increases, and that's why your hardness increases, and this vulcanization is because of your sulfur atom. Okay, so the vulcanization of the natural rubber takes place by its treatment with the sulfur one. Okay, is it clear? Okay. Okay, then let's move to the question number 3. In question number 3, what is asked, the in it is asked, based on the arrangement of the side group in the polymers, which of the following is true? So according to the how your side group is arranged in the polymer, so which of the following is it? A part is isotactic polypropylene has the lower thermal conductivity than of the atactic polypropylene. In B part, isotactic polypropylene has the larger thermal conductivity than that of the atactic polypropylene. In C part, isotactic polymer has the lower degree of crystallinity than that of the atactic polymer. In D part, isotactic polymer have the larger degree of crystallinity than that of the atactic polymer. So based on the based on the this arrangement of the side groups, we have the three type of the polymer. One is the atactic one, another is there is the isotactic one, and third one is the syndiotactic one. That is the syndiotactic one. So what happened? So this my the side group element or the side group if it is arranged in the random one, so that belong to the atactic one. And if it is arranged on the one side of the one, that belong to the one side, then that belong to the isotactic one. And if it is arranged in the form of the alternative form, so that it will belong to the syndotactic one. Okay, you can see from here, this in atactic we have this red color with the carbon, blue is hydrogen, and the open circle is the chlorine vinyl side group. Okay, if you can see here, this your hydrogen, the placement of your hydrogen, and the this vinyl side group, this is not fixed, these are the random. There is no here, see here hydrogen is here, now two hydrogen are here, now here the Cl1 one is hydrogen again here, so there is no arrangement, there is a random arrangement of the side group. So if this is a random arrangement of the side group, so it will be the atactic one. And if I talk about the isotactic, in isotactic we side group have on the same side. See, you can see the hydrogen, if this is the my carbon atom, this one is my carbon atom, if I see this carbon, so my hydrogen, this hydrogen on the front side, this hydrogen on the front side, and again this hydrogen on the front side, and you can see this your vinyl side group is on the back side. So your hydrogen is on the front side and your chloride vinyl this side group is on the back side. So we have a proper arrangement where one side, this one side group is on the one side and another in the other side of the day. So this will belong to the iso means same, and the same kind of the arrangement here. But if I talk about the syndotactic we have the, you can see here the your this vinyl side group is at the back one, and if you see here, then your this vinyl side group is at the front side. Now they are regularly, first they are in first one it is at the back one, in the another case it is in the front one, in the third one it is again at the back, and this also in the fourth one it is at the front side. Same is the for the hydrogen one, first in the front, then back, then front, then back. So these are the regularly alternative arrangement of the side group. You can see here also, because I mean the your this side group first in the back side, then on the front side, then again the back side, then again on the front side. So that's why this is the alternative arrangement of your side group. If there is alternative arrangement of the side group, then it belongs to the syndotactic one. Okay, so this is about the arrangement of the side group. Now let's come to the question one. In the question one, it is asked, isotactic polypropylene has the lower thermal conductivity than that of the atactic polypropylene. If you compare in the isotactic and the atactic, which one is having the low thermal conductivity? So if you know low, I mean conductivity, what is the thermal conductivity? First point is the what is the thermal conductivity? Thermal conductivity is the property where the heat is flowing through the material from one point to the another point. How easily my heat is flowing, that is defined by the thermal conductivity. If there will be the I mean the regular arrangement of the atom, I mean there is a crystallinity, or we can say that this is the crystal, so that there will be the higher thermal conductivity. If there is the random arrangement, or the this is the random arrangement, so uh, this is the higher thermal conductivity. If this is the random one, so then there will be the lower thermal conductivity. Okay, so this is way the your thermal conductivity is defined in your isotactic and atactic. So if I consider the isotactic and atactic, you can see in atactic it is the random arrangement. So they will be having the atactic ones will be having the lower thermal conductivity as compared to the this isotactic and the syndotactic one. And also if I talk about the here, because in the C and D part they have talked about the crystallinity also. So crystallinity is higher in the iso, because there is a regular arrangement of their regular arrangement, so this is higher in your uh, crystallinity will be higher in the your isotactic compared to your higher in the isotactic compared to the atactic one. Okay, so this thing we have discussed. So this is because so the hey this my atactic is having the lower thermal conductivity and your isotactic is having the higher crystallinity. So if you see from here in these options, so which will be the correct one? So iso in A part isotactic having the low thermal conductivity than that of the atactic one. No, this is having the isotactic having atactic having the lower one, isotactic having the higher one compared to the atactic one. So B is the right one. If I go to the C and D part, in isotactic polymer having the low degree of crystallinity than the atactic. No, isotactic having the higher degree of the crystallinity than the atactic polymer. So D is the right answer. So for this one we have learned about this. If my arrangement is the if my arrangement is regular, I mean they if they have the crystallinity, if they have the crystalline, then there will be the higher thermal conductivity one. If there is the randomness, then there will be the lower thermal conductivity one. And in isotactic we have the regular arrangement of the side group. In atactic in the this is the random one. So that's why your atactic is having the atactic is having the lower thermal conductivity and the lower crystallinity as compared to the isotactic one. Okay, is it clear? Okay, okay, then let's move to the question number 4. Okay, in question number 4, so which of the following polymer have the random arrangement of the side group? As we have discussed in the last question, we have the random arrangement of the side group belongs to the atactic polymer. So A is the correct answer. Atactic polymer. And as I already discussed, atactic polymer has the random arrangement of the substituent groups on the main chain. This is because can be placed. I mean, these substituent like the methyl group in the polypropylene can be placed either on the side of the polymer backbone without any regular order. And because of this regular order, atactic polymer usually amorphous. I mean, amorphous usually means the less crystallinity and having the low density. Because of the amorphous, they are amorphous, so lower density, lower melting point, and they often do not crystallize well due to the lack of regularity in their structure and leading to the material that are usually softer and the more peelable. Okay, if I talk about the isotactic, in isotactic they are the side group are on the same side of the polymer chain, and this regularity form a highly symmetrical structure. And because of this highly symmetrical structure, it is having the high crystallinity. Okay, and it allow the polymer to pack closely together, because they are having the because everything is in the regular pattern, I mean in the symmetrical pattern, so they can pack closely together, or that's why they are often tougher and having the higher melting point and the more rigid as compared to the atactic polymer. We have the another one, the syntactic polymer. In the syntactic we have the alternative sides in the regular pattern along the polymer chain, and these polymer also can achieve the high level of the crystallinity but with the different physical property than the isotactic polymer, because they are now the physical properties will be different, because we have the different side group are having the alternative arrangement one. Okay, that is compared to the syntactic polymer usually have the property somewhere between, because of the isotactic and the atactic, and such as the moderate melting point and the mechanical strength. So these all about with the three kind of the arrangement of the side group one is the isotactic, atactic and the syndotactic one. So if I go with the crystallinity order, uh, because syndiotaptic we can achieve the high level of the crystallinity, but we have the different physical this physical property than the isotactic. In the crystallinity, which one is the higher one than the this? We have the isotactic one has the higher crystallinity. We can achieve it in the syndotactic, but there is a different physical property. If I talk about the melting point, which one is having the melting point? Then the isotactic is having the higher melting point. Which one is having the higher toughness? The same again, this crystallinity, this isotactic one is having the higher toughness in the material one. Okay, so this is all about the arrangement of the side group in the polymer one, and we classified them into the three category one. Okay, now let's move to the question number 5. In question number 5, which of the following is an are correct? Thermostat polymer soften upon heating. And in the B part, the thermoplastic polymer have the linear and the branch structure. C part, vulcanized rubber, epoxies and the phenols are in the class of the thermostat. In the D part, the cross-linking is the characteristic of a thermoplastic polymer. Okay, we already have discussed about the thermoplastic and the thermoset or the thermosetting plastic. In the last class today, we will I will give you the just an overview. In the thermoplastic are the basically that get softened upon the heating, but the thermoset does not soften on the heating. They get set after the heating. This is having the reversible process, and this thermoset is having the don't be confused with the difference. So let me write as the thermoset. So this is the irreversible process one. Thermostat, thermoplastic is generally having the long chains, this linear or the branch structure one, and the thermoset is having the 3D structure one. And this is done by the by adding the polymerization, and this is the condensation polymerization one. It can be reshaped and reused because it is the reversible. Then it can be reused and the reshaped one, but the thermoset we can't be reshaped them. Also, these the soft and the weak and the less brittle one, but here the thermoset are the hard and the strong one. In the thermoplastic are the soluble in the organic solvent, but this thermoset insoluble in the organic solvent. In the same part, the thermoplastic reclaimed for the waste because it is the reversible again, and it can't be okay because once it is used, so it will can't be used for the another shape or also, so we can't use them. This is the irreversible process. So this is all about the thermoplastic and the thermoset. Now in the first in the question, this in question in the E part they have asked the thermo, so you have to tell the which of the following statement are the correct. In A part, the thermoset polymer soften upon heating. Yes, upon soften upon heating. Yes, we already know thermostat does not soften upon heating. They set even they are having the reversible process, irreversible process. So thermostat generally set upon the heating. Thermoplastic generally soften upon the heating. In the B part, in the thermoplastic polymer have the linear and the branch structure. Yeah, it is true. The thermoplastic polymer have the linear and the branch structure one. In the C part, the vulcanized rubber epoxy phenols are in the class of the thermoset. Yes, the vulcanized rubbers because they have the now the cross linking. We can't change this because this is not the reversible process. So the vulcanized rubber epoxy phenols are in the class of the thermoset. In the D part, cross-linking is the characteristic of the thermoplastic polymer. No, thermoplastic is not a no. This cross-linking is not related to the thermoplastic. It is related to the thermostat because this cross-linking is not a reversible process. It is a irreversible process. So this is belong to the thermostat polymer one. Okay. I hope you can you understood this thing how you distinguish between the thermoset and the thermoplastic one. Okay, So this is all about the question number 5. Let's move to the question number 6. Okay. So till this point, if you have any question, please let me know so that I can, we can solve this question if you have any. Do you have any question till this point? No? Okay. Okay, I'm hoping it is clear to everyone. So let's move to the question number 6 again. So ba- based upon the plots shown here, choose the correct choices among the following. It is here. This is A, this is the A part, this is the B part, and the C part. So we already discussed about the this elastomer, elasticity basically, and the rubber cases also, and the brittle and plastic we also. So we have to tell how your what is your A, B, and the C part in the. So in the first, this is this in A part, this is stress is increasing. Uh, that is increasing at a particular value of the strain. This is there is the higher this high slope is there. If you see in the B curve, this is slowly, the changing, it's a changing with the strain, but in the C, it is changing with the strain also, but it is going to the higher strain. In the B part is going to the lower strain. In the A part, in A also, it is going to only some restrictive value of the strain also. So this A molecule can't withstand the your strain. In B it can withstand, but a something particular value in the C part, C polymer, that can withstand the make this the maximum strain compared to the A and the B. So in this part, in the A part, it is said that in curve A denote the brittle polymer. So what will be the brittle polymer? Basically, if it get brittle is when you apply any strain, it can't withstand that strain. It can't afford that strain, so it will be the brittle one. Or you can see here also, this is not this can't withstand or the afford this the strain. So yes, your curve A is the brittle polymer. In the this curve C denote the elastomer. Yes, your curve C is denoting the elastomer. Elastomer are basically all of the your rubber like structure, so they have the elasticity and they can withstand your strain and strain also. So yes, C part is correct. So C denotes the elastomer, and because elastomer having the elasticity, and C is having compared to the higher elasticity compared to the A and B. So C is also the correct answer. In the D part, excellent bonding and the recoiling nature are the characteristic of the elastomer. Yes, excellent bending. How much it is bending and it is recoiling. So that nature of the elastomer. So D is also the correct answer. So A, B, and C and D all are the correct answer corresponding to the this figure. Also, and if I summarize this thing, elastomer is a polymer that deform when stressed and return to its original shape when stress is removed, similar to the rubber one, and they are known for their elasticity, which come from their coil structure. Here are the some properties of the elastomer. Elasticity, elastomer have the weak intermolecular forces and the low Young's modulus. Deformation, elastomers deform significantly under the small mechanical bond. Elastomer having the poorly crystallized, but become the more crystallized when stretched one, because now they are in the particular they when we stretch, they become in the particular arrangement. If it is not in the stretch mode, so they are there in the random one. So elastomer are used in the smart textile, wearable devices, soft robots one, gloves, implants, and the po- uh, prosthetics one. So these are the elastomer rubbers. Also the same thing, rubbers, polyurethane, PDMS, latex one, the Also, so this is all about the an elastomer are the usually the thermostat requiring a curing process of the rubber involving the heat and addition of the sulfur and the other equivalent curative, because elastomer are basically this is the second stage of the natural rubber. There is the some addition of the sulfur agent. There is a slight cross link is in the your elastomer that we have discussed in the last question, I guess, last or last to last question. Yes, in the this one or the yes in the in question number in question number 2 we have discussed. So elastomer having the slight cross linking one. Okay. So this is all about the question number 6. Let's move to the question number 7. In question number 7, in question number 7, that is the it is asked the X-ray can penetrate into the metal because of which of the following the characteristic? Because of the high energy, lower wavelength, shorter wavelength, and the long energy. So if you see, this is the spectrum of the electromagnetic one. So this is the frequency range. So here the my frequency is increasing. So here this region belong to the radio waves. This is the television. This region the radar and the microwaves, and this is the infrared, and this is the UV that we talk about, the UV visible light. This is your no, this is the visible one, and this is the UV one, ultraviolet, X-rays and gamma rays. And if I see in the frequency order, so gamma ray is having the higher frequency one. So frequency is inversely proportional to the wavelength. So this is also gamma ray is having the higher frequency, so they are also having the shortest wavelength one. And then in the ascending order, then it will come the X-rays, then UV waves, then visible, then infrared, radar waves, microwaves, and the radio waves. And corresponding to the energy also, they are this frequency is related with your energy also. So the gamma rays having the higher voltage photon energy, then your X-rays, ultraviolet, UVs, then the visible, then the infrared, then the microwaves, television, and the radio waves. So is in the question, X-rays can penetrate into the metal because of the which of the following characteristic. So X-ray is lying in this direction. So why they can penetrate into to metal? Which of the following characteristics? Is it having the because of the high energy? No, gamma ray is also having the higher energy because they are having the shorter wavelength. That's why they can into the they can penetrate into the metal one because of their shorter wavelength. X-rays are having the shorter wavelength compared to that one, and these are having the higher energy compared to the UV or the visible or the radio microwaves energy. They are having the higher energy, so that's why your X-rays can penetrate into your metal one. Okay, so this is the theoretical question. This is over. Let's move to the question number 8. In question number 8, suppose there is a vacant electronic site in the K cell, and if an electron from the L cell fill the vacancy in the K cell, then it emit which of the following radiation? Okay, you already know that the when your if you provide an energy, then the electron will remove from the K cell, and that there will be then vacancy created in your K cell. If this is K cell, L cell, K having the difference, so K, M, L, M, N. So if there is vacancy created here, then the electron that are present at the higher energy, they will see this vacancy and will come to this point. And the whatever the there is the energy difference, so that corresponding to that wavelength will be generated, and that the I mean the photon that is generated of that corresponding wavelength, that will give you the X-ray. So this vacancy, this K cell vacancy, can be filled to the any of the cell that is at the higher position, because this the higher position of alpha. Now it's here the electron is coming from the L cell. If it is coming from the L cell to K cell, so what will be the which of the following radiation will it emit? It will be the K alpha, L alpha, and the K beta, or the same. If it is, because V alpha having the 3 K, L1, L2, and 3, if it is for the M1, so it depend upon from which cell to which cell it is coming. If it is coming to K cell from any of the higher one, then it will be the K. Alpha, beta, gamma, that will be defined by the from which cell, from the which energy level it is coming. So if it is coming to K cell, then it will be the K1. If it is coming to L, then it will be the L, alpha, beta, gamma, whatever it is. And so here, so it is coming to here, it has the vacancy in the K cell, then the electron will come to the K cell, and from where it is coming? It is coming from the L cell, the next cells, from the next cell to the K cell. It is coming from the L cell, so this will be the, it will come to L to K1. So electron will come from here to here one. So this will come into, so it will be the your, okay. So it is coming to from L to K1. If it is coming L to K1, then that will be the alpha. If it is coming to L2 or the for the higher one, then it will come to the K beta, then again the K gamma subsequently ones. But it is coming to L to 1, L to K1, so that will be the alpha, and it is coming to K, so it will be the K alpha. So the radiation will be the K alpha 1. So A will be the right answer. Okay. So this is about the how we name the radiation. If it is uh, to which energy level it is coming, that will define the this your K element. Alpha beta defined by the from which level it is the electron is coming. So from which level it is coming, so that is defined by the your alpha beta and the gamma one. Okay, here in this question, in it is coming from the from the L cell to the K cell. K cell, it is coming to K cell, then it will be the K1, but it is coming from the L cell, so there will be the energy difference of the L minus K. So the this radiation will be the K alpha one. Okay, now let's move to the question number 9. In question number, which of the following are the true? In A part, X-ray is the fixed in case of the Lee diffraction method, and the B in the Lee diffraction method is generally for the powder one. In the C part, X-ray wavelength is fixed in case of the rotating crystal method. In D part, the diffraction angle is variable in the rotating crystal method. So you all know that we have the X-ray, we have the different method from the way we can get the X-ray. So here it is asked about the Lee diffraction method, and the another one is the rotating rotating crystal method. Okay, we will discuss first one by one these, and then we will come to this question. And also we have the single powder method, also we call that the powder X-ray. In the Lee diffraction uses the white X-ray radiation that is having the range of the wavelength, but in Lee diffraction, we have the my crystal remain the stationary during the exposure, and this is used for the determining the crystal orientation and the symmetry of the single crystal. Generally used for the single crystal. This is the experimental setup of the lead method. So here this is the your X-ray source, and is it coming, this is for the reflection one, that is the film from the reflection whatever if it is coming, but this we have the slit here, so the X-ray will go. This is because of to remove the splitting of this X-rays, I mean the broadness, or the we have decreased the aperture for the X-rays, so it will be focused one and more focused one when this I mean fall incident on your crystal specimen, so there will be the reflection, it moves the, so if the x-rays that are we have the reflection as well as the transmission, also transmission radius, so there we have put the setup for the transmitted radiation. There is a film from the transmitted one, this is the transmitted, and if any of the x-rays that is come from the reflection one, back reflection one, so there is a film attached to here also, that is to collect the back reflection intensity. So this is the experimental setup of the Lee method, and if you see the, this is the diagram showing the arrangement of the spot in the Lee photograph of a simple cubic structure. They have taken the simple cubic structure and they are getting the structure of this one, because it is, because we have the transmitted as well as the reflected one, this reflected light also, so we get the this kind of the ellipse kind of the structure in the pattern one. Okay, next one is the rotating crystal structure. In this we use the only the monochromatic one, and here my crystal is rotating, because in earlier case we have the different range of the wavelength also, and my crystal is fixed. Now my here the crystal is rotating, it is rotating about this axis, so this crystal is rotating this, and this will give you the crystal structure of basically the x-rays used to determine the crystal structure and the orientation of. So this so this use the monochromatic x-rays, we have the only the single rays of X, and crystal is rotated during the exposure, and its application is to measure the lattice parameter and the index and reflection of to determine the crystal structure. This is the setup for the rotating crystal method. This is the incident wave, and here this is my crystal one, and this crystal is my moving along, and this we get the, we have the film, we have attached a film here, and from there the diffraction will be, and we get the pattern, or we can say this is the another setup, the same thing. We put the kind of the in the three-dimension one in the all the direction one, because it is rotating, and we have put the cylindrical form of the detector here, so will get the corresponding ring here. If it is at this angle, at the particular angle, again here we will be have the ring, and we will the, if we open up this and see this, so there will be the, this is the one that is not that is completely transmitted one, they are the diffractive one, so this will become this kind of the structure. So the pattern for the rotating crystal thermal will be the this like of the spotlight, we can say this will be the this kind of the structure is for the for your rotating crystal method. Okay, if I summarize the both the method, also the powder one, in the method Lee method, my wavelength is the variable, because we have used the range of the wavelength, and my angle at which it is incident. From here you can see we have fixed this angle, because it is a different wavelength, but it is fixed here. I mean whatever this will give at the particular angle, there is no change in the angle, so my angle is fixed, only the wavelength are getting the, because we are getting the everyone, there is no filter for the wavelength one, so there is my angle is fixed, but the and specimen we use the single crystal. In the rotating crystal we have the wavelength fixed, by my this my crystal is moving, and it is also used for the single crystal. And the powder method there, where my wavelength is fixed, my angle is variable, and that we use for the powder one. Okay, so these are the three different type of the X-ray method. If you I come to the question, in the question number in question number 9, it is asked, so in the Lee diffraction method, will it the X-ray wavelength is fixed? In Lee diffraction method, as I already told you, my X-ray wavelength is not fixed, that are using the range of the wavelength, so this is not correct one. In the B part, Lee diffraction method is generally used for the powder. No, Lee generally method is for the single crystal one. In the C part, they have used the X-ray wavelength is fixed in case of the rotating. Yeah, in this part, rotating crystal method, my X-ray wavelength are the fixed one. In the D part, the diffraction angle is variable in the rotating crystal method. Diffraction method is variable in the so yes, it will be the diffraction angle will be the variable in the rotating crystal method. So your C and D are the correct answer, and you can know, if you know about the what is the your Lee diffraction method and the rotating crystal method, then you can find out in which case you're in the Lie, basically you have the crystal is not rotating, only the we have the different we have a not the different, we have the range of the wavelength. And the in rotating crystal, as the name suggests, the my crystal is rotating, but we have the wavelength fixed in the this thing. Okay, so this is all about the question number 9. Let's move to the question number 10. Just read it and we will discuss it. Okay, so in question number 10, so the question is the condition for the nickel to be used as a filter material for filtering the K beta radiation from a copper target. As you know that we got the continuous spectrum of the wavelength for this one, but if we this is for some voltage, and if we increase the voltage, then it will shift to the lower wavelength, and the intensity will increase mu by alpha. This is lambda, and at particular voltage it will we have get a characteristic characteristic x-rays, sorry, characteristic x-rays. So there will be the for the Kuiper one, so we have to put the, because in this one we use the particular, as I already told you, we generally use the powder one, the powder method. So we use the I mean the single intensity peak. So we need the monochromatic wavelength of the X-ray. So we need only the one type of, so not the variable range of one. So that is we use also, we need the filter just to filter out only one characteristic peak of the this your copper one, the K alpha. So we have to remove your K beta for the filtering, because this is my K alpha and this is my K beta one. So why it is K beta is lying here and this K alpha is lying here, we will discuss this thing also. But first thing is, I mean, how the condition, whatever the change, I need also here the condition for the nickel to be used for the filtering the K beta. Now we have to remove this wavelength. This wavelength we have to, we want only this K alpha one. This is having the higher intensity K1. We want only this K alpha wavelength. We don't want this K beta one. So we have to remove this one. So how, what will be the condition if I nickel having the this kind of spectrum? So what will be the condition for the nickel one, so that we can filter out this the K beta wavelength? To okay, so to use the nickel ELF effectively as a filter, its K base should be positioned. So we want this wavelength only, K alpha one we want. So my A's, I mean this nickel edge should be such that, so that it can have only this value. So it should not have this one. So my this A's this nickel edge should be lying in between them, between the alpha and the beta one. So similarly, it is said in the its Ks should be positioned such that it absorb, yeah, it absorb this one, and we get only, because if anyhow this K beta will be absorbed, then we will remain with the only the K alpha. So therefore, this nickel age should be higher than your nickel age should be higher than the K alpha one, but lower than the K beta one, higher than in the alpha. But here, if you say that this nickel age should be positioned between the, should be positioned between the K alpha and the K beta. Okay, and the this is having the lower energy. Nickel age should have the higher wavelength than your K beta, but lower wavelength than your K alpha line. Okay, so it should be such that it is lying between them, but it should be the wavelength, because here it is my wavelength, so its wavelength should be the, it is higher, this age should be higher than the K beta, but is lower than the K alpha, so that it can absorb the K beta light and can we will have with the remain with the K alpha line. So here it is asked in the in term of energy. If I say in the term of energy, so in term of energy it will be the energy. So this is K alpha is like the lower and lower, this is, but it I mean the this is having the higher one at the higher wavelength, so this will be the having the lower energy K alpha. This is of the copper one. Then we have the energy of the K alpha nickel one, and then for the almost K beta the copper one. So my energy should be like that, that it is higher than the K alpha of the copper, and the lower than the K beta line of the copper one. So according to this one, so it will give you the, it should be the higher than the higher than the K alpha and lower than the K beta. So your B part will be the correct answer. Okay. So it should be such that it absorb the lower wavelength, but it can't absorb the higher, because at the lower wavelength it can absorb. So it should be positioned between them. If we want only the K beta one, because the K beta or the note, it should be somewhere such that, I mean, if it is not about the K beta and the alpha, it should be like that. The smaller wavelength will get absorbed, and the higher will remain with that thing. So we have to position such a filter such that the smaller we can absorb, and the we will remain with the higher wavelength line. Okay. Okay, this is all about the question number 10. Let's move to the question number 11. Okay, so equation number 11, which of the following is and are correct? Diffraction happen in a specific direction along which the constructive interference occur. Okay, how this your this constructive interference happens. So scattering is a random phenomena and takes place in the all the direction. In the C part, the reflection of the visible light takes place in a thin surface layer only, and the D part, the reflected and the diffracted rays both can be the 100% in term of the intensity one. Okay, so what is the diffraction, scattering one? So we will discuss first one by one this one, and then we will come to back to the discussion. Reflection is basically the light bounce off a surface and head in the same direction as if in the straight line. If this is the my surface, and if it is coming like this way, so it will get will head in the same direction, and then it head back into the bounce off, and they will head back in the same direction, because my angle of incidence will be the angle of reflection. It is the law of the reflection that should your line follow. Okay, and reflection is basically, this is reflection generally is basically as a result of the particular nature of the matter. Scattering is basically light reflect off the piece of an object and scatter in the different direction, and the wavelength of the scatter light can change in the shorter wavelength scatter more than the your longer wavelength, and scattering of the light is because of the your wave nature of the material one. Okay, so now in the A part, it is cast that the diffraction happen in a specific direction along which the constructive constructive interference occur. Yes, diffraction only happen to the in a specific direction. It is not it will happen to this. There will be the intensity should be say, it should be say, so that there will be the along with the your construction interference occur. That matter for the diffraction pattern. In the B part, the reflection. So A is the correct answer. In the B part, the scattering is a random phenomenon and takes place in the all direction? Yes, scattering is a random phenomenon and it takes place in the all direction. In the C part, the reflection of a visible light takes place in a thin surface only. Yes, reflection generally of the visible light takes place at the thin surface also only, and the reflected and diffracted rays both can be the 100% in term of intensity. No, because the reflected is not necessary, or reflected and the diffracted ray are always be the 100% of the whatever the instant intensity of the incident wave, it can't be same in term of the reflected and the diffracted wave. So it is not correct one. So D is the not the right answer. The it is not necessary condition for that the intensity should be same as the incident intensity one. Okay, so let's move to the question number 12. In the question number 12, the wavelength of the radiation that could be used for the diffraction to happen from a plane of a atom in a material can be computed as the maximum interplanar spacing that is observed is the 3 angstrom. Okay, so maximum interplanar spacing that observed is the D is your basically the 3 angstrom, and you have to tell what of the order of the radiation. I mean, that's depend because we have this double slit experiment is basically of is done with your the UV visible light, and we saw that the we get the visible if my slit is of the order of the this visible light, and we can get the this interference pattern for the visible light. So the same idea come from there, and we find out that if we take the crystal size, size, the distance between the atom, that is order of the any radiation that is having the same order of the crystal size, that can be used to get the structure, or the I mean to get the the crystal structure of that material. There we so here if it is the interplanar interplanar spacing, the maximum the interplanar spacing is of the 3 order, so what will be the order of the wavelength that we use for the diffraction to happen one? So if because we all know the Bragg's law, I mean this is of it should be of the same order, but what if the Bragg's law is equals to 2d sine theta is equals to n lambda. This is the wavelength of the radiation, and this is the sine theta, that is the angle of the diffraction one, and d is the your interplanar spacing one. And you know how this formula come into the picture. We there is the path difference between the reflected I mean the diffracted waves, and there is the path difference between this is the distance is the d sine theta, and for the constructive interference to happen, we need this path difference should be of the order of n lambda. So the total path difference is the 2d sine theta, that should be equal to the n lambda. So this come, so d is your interplanar spacing, and n is also your d here, it is the of the order of 3 angstrom. So n could be for the first order, if I consider this n equals to 1, and the sine theta can have the maximum value as +1 and the minimum value as the -1. So this lambda will be of the order of 2 into 3, that is they are around the order of the 6 order. Okay, so your the wavelength of the order that can be used for the diffraction to happen from a plane of the atom in a material can be of order of the 6 angstrom one. Okay, so you have to find out how the order of the order of the, if somebody has given you I want to examine this object one. So first you know the, if you know the interplanar spacing or the size between them, the plane that can diffract the light one, or the radiation, whatever the kind of the radiation we can use. So we should know first earlier, our aim is to find out the distance or the interplanar spacing in that object, so that we can choose the what kind of the wavelength we can use for the to examine there the crystal structure of that body one. Okay, so this is all about the question number 12. Let's move to the question number 13. Okay, so in question number 13 it is asked which of the following is an are correct. A part in Bragg law equation, n is the order of the reflection. What is the Bragg law? So Bragg law states that when your X-ray hit a crystal at a specific angle, so this is the my specific angle and this is the my incident plane, and the wavelength, the reflected X-ray will be intense one, and this happen when the scattered X-ray interference constructive. So your reflected rays X-ray will make a interference, so there will be the your Bragg's reflection one. So the what will be the Bragg reflection one? Bragg law equation, that is the 2d sine theta equal to n lambda. N is the order of reflection. It can only have the integer value, that is the 1 2 3 4 5 and so on. Okay, so in the A part, in the Bragg law equation, n is the order of reflection. Yes, it is correct. In the B part, it is asked B part, the first order diffraction. N equals to 1 represent the first order diffraction. N equals to 2 is the second order diffraction, and n equals to the 3 is the third order, okay, diffraction. So it will keep going on, and n will be the nth order diffraction. Okay, so in B part, it is a in the first order diffraction. This plane is equivalent to the second order this plane. So this plane, if we have the HKL, this D is, because of the simple cubic, if I say this D is basically A is equals to 2 H square plus K square plus L square. D is basically, this is the atomic distance, this is the interplanar spacing. Okay, or yeah, this is the my lattice parameter, and HKL are the index of your plane one. So in the first order one, if because n this is depend upon 2d sine theta equals to n lambda, so the for the this plane for 1 0 1 0 0 plane, this your d will be the 2a sine theta, and this is of the first order, then equals to n lambda. For the 2 0 0 plane, it is like that 2, this become the a into 1 root of 2, I mean because d will be the a divided by 2 square plus 0 square plus 0 square, square root will cancel out with the square, and it will become the d is equals to a by 2 sine theta, and it is of the order of is equivalent to the second order 2 lambda. So this will cancel out and it will remain the a sine theta equal to 2 lambda. Earlier we are having the a sine theta equals to a sine theta equals to lambda. So both are not correct. So B is the incorrect statement. Comes to the C, in the second order of a 1 1 0. So second order of, if this is of the second order, so this will cancel out and this will give you a sine theta equals to lambda. So this is the new one and is equivalent to first order of 2 0, and it is of the first order, so n will be the 1, so this will cancel out, and this is giving the same is equals to a sine theta equal to lambda. So these are both are equal, so the second order diffraction of 1 0 0 plane is equivalent to the first order diffraction of 2 0 0. So your C is the right answer. And in the D part, the plane 1 0 0 2 0 0 0 are the plane part, because in the earlier case, in the crystal structure, we already discussed this thing. We have the plane that are the parallel plane, they will have the index are the same. So 1 0 0 2 0 0 3 0 0 4 0 0, or these are the my parallel plane. If this is 1 0 0, this is 2 0 0 3 0 0 4 0 0, and so on. These are the my parallel plane one. Okay, this is all about the question number 13, and let's move to the question number 14 1. Okay. So, what does this SWL stand for? If you see in this figure, so in this figure, what this SW, this is SW stand for. First one is the A shortest wavelength limit, B side wavelength limit, D short wavelength limit, D is the standard wavelength limit. So what is your limit? So basically, if I tell you this SW is your short wavelength limit. What is this short wavelength limit? If you this distance, if this is your intensity and this is wavelength, if you see this is the particular wavelength where your intensity is zero for a given applied voltage, because these are the different voltages. This here is the different voltage, here it is the different, or here it is different. So these are the different for the particular, for this voltage this is my SWL, for this voltage this is my, this point is my SWL, for this voltage this is my SWL. So SWL is the that limit, the limit where the where your intensity become the zero, because if I plot the my intensity versus wavelength, so we get the this kind of the graph. Okay, so where your intensity becomes zero, so that wavelength will be your SWL limit. So if you see from, if I'm increasing, because here in this direction where my voltage is increasing, if this my voltage increasing, so my SWL limit decreasing is going toward the zero thing. Is so if my voltage increasing, the SW move to the left, and intensity of the all the wavelength increases. If I'm talking not of the all the way, if because if my voltage increasing, if I see this distance, let's say this is my particular wavelength I'm looking, and the how this is increasing voltage, so the my intensity is increasing for the all the wavelength here increasing. So as my voltage increases, your SW will move to the left one, and the intensity will increase one. In the next one, as the voltage increasing, the kinetic energy of the bombardment electron increases. Yes, because EV is equals to this your kinetic energy is basically that is the energy providing. So that kinetic voltage increasing or kinetic increasing, and which lead to the lower value of SWL1. As voltage increase, the distribution intensity or the lift toward the higher. And you can also see that the maxima, this maxima is also moving with your voltage. If it is with the increasing voltage, then your this maxima value of maximum lambda, like the maximum wavelength, that will also shifting toward the left one. Okay, shifting toward the lower wavelength. This maxima here it is, now it is moving here, now it is moving here. So this also moving toward the lower wavelength. So this is with the increasing the wavelength. So this SWH represent the short wavelength limit, that is your C part. Okay, so this is all about the SWL. Let's move to the question number 15. So in question number 15, what happen when the voltage of the X-ray tube has been increased? So what will happen when the voltage of the X-ray increase? The A part, the intensity of the all wavelength increase. Yes, if you see for the increasing voltage, if I'm this in this direction, this is voltage increasing. I'm talking about the different curve. So these curve, the different curve, that is the my voltage is increasing. So my voltage is increasing, the intensity of the all the wavelength increasing. Yes, my the intensity of the all the wavelength increasing. In the B part, the SWS shift toward the shorter wavelength. So for this voltage it is here, for this is here, this is here, 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 here. So with increasing voltage, this SWL moving toward the lower wavelength. Yeah, so this SWS shift toward the lower wavelength. So B is also the correct answer. In the C part, the position of the maximum shift toward the longer wavelength. The position of this maxima, this maximum wavelength, this position, is it the position is moving toward the longer wavelength? No, it is moving toward the distribute toward the lower wavelength. or the this is in the next part it is the SWL shift toward the lower. No, it is so C and DR is not the correct. Only A and B are the correct. SWL shift toward the shorter wavelength, and the intensity of the all the wavelength increases if we increase the voltage one. So this is the intensity graph of the with the wavelength one. Okay, let's move to the next question. In question number 16, which so we have the same graph that we have earlier, but in this question it is asked, so which of the following is the correct one in a given plot? Two sharp peak, because there are the two sharp peak. This is the one sharp peak and another is the this two sharp peak. Okay, so in this two sharp peak, we have to tell the correct statement regarding these two sharp peak. In the A part, it is these belongs to the characteristic radiation. Yes, we all know this. If this is for the copper one, this is the K alpha and this is the K beta, and the K alpha and the K beta are your characteristic radiation, characteristic X-ray or rather radiation one. Okay, so A will be the right answer. Okay, the in B part, K beta is at the higher wavelength. If you see, this is your K beta, and K beta is at the higher wavelength side. No, this is at the lower wavelength side. So this is not correct one. K beta is the lower side, and the next one is the K alpha is at the higher side. Yes, this K alpha is at the higher side, and K beta is at the, this should be the lower one, the lower wavelength side. Yes, then C will be the right answer. In the D part, this is due to the diffraction from the X-rays. No, this is not due to the diffraction of X-ray. This is the graph for the this how the your intensity is behaving with the this lambda one, because intensity is also changing where there is the attenuation factor in the intensity as it move with the distance, so they are intensity also vary, and this we have plotted with the different voltage. So this is not the diffraction from the one. So one body, if you don't have this plot, and you somebody asks that the K beta is the higher, because we know that the K alpha is basically that is the light coming from, let's say this is my K L1 and L2. Okay, so K alpha will be the X-ray when radiative when your electron move from this K L1 to K. So that will be the K alpha, and K beta will be the from L2 to K. So K alpha, the energy for the K alpha will be the corresponding light when the energy is your energy E L1 minus E K, and K beta will be the E2 will be the E L2 minus K. This energy is this energy gap is different, so that is having the higher energy. So this is your higher energy, so that's why this K beta line is at the lower wavelength. Okay, so that's why your K beta occur at the lower wavelength as compared to the K alpha, because K alpha is having the smaller energy and the higher wavelength. So always your alpha line will be at the higher energy, higher wavelength, and the beta will be there the lower wavelength. Okay, now this, because now you have from these type of the question you have already confirm this thing, because as we increasing the, because we get the characteristic. यार तुम्हारा दिमाग खराब है क्या? हमारी मीटिंग चल रही है, थोड़ा धीमे नहीं कर सकते? तो यार ये क्या मतलब, एक बार बोल के देखो ना, तुम्हारी दोस्त से फोन करके देखो। वो बॉल भी कोई रिस्पॉन्ड ही नहीं करे क्या? तो एक बार थोड़ा धीमे कर लो, हमारी मीटिंग चल रही है। या तो गार्ड को बुलाओ, ऐसे पीटने से थोड़ी ना होगा। Sorry, so we have sorry for the this inconvenience. So as the voltage increases, we found that we get the characteristic peak for the I mean otherwise we will get the for the lower voltage we get the continuous peak of the x-rays. These are the continuous we get the x-ray, but the for the if we increase the voltage, then we will get the characteristic peak, that is the k alpha and the k beta 1. And also with increasing the voltage, this your maxima will shift toward the lower wavelength, and your always k beta will be at the lower wavelength as compared to the your k alpha. K alpha is the more intense peak and it is lying at the higher wavelength one. Okay, so this is all about the this graph, intensity versus wavelength graph, and how this is related with the voltage, and how this SWL is shifting toward the lower wavelength if we increase the voltage one. Okay, let's move to the question number 17. In question number, so now we know the SWL for the this voltage. This is the 20 kilovolt tube voltage we are having. So what is the wavelength for the this corresponding the wavelength one? Because we know this SW is the very the intensity. So whatever the energy we are giving, that is used. I mean uh, there is no intensity, so the energy that is we are giving the electrovolt will be having totally there. Your this will be the hc lambda, the voltage that is responsible for the radiation for that line. And if I know, because your we know that this SW is the minimum wavelength where your intensity is 0, so lambda will be the hc by e. And if you put the h value, that is s 3.3 6.6 into 10 raised to minus 34, and c is equal to 3 into 10 raised to power 8, e is equals to 1.8 into 10 raised to power minus 9, and the v. If you put these value and substitute this one, and you will get that this your lambda minimum, your this lambda SWL will be the 1240 divided by the volt, and this is your in the kilovolt only, electron kilovolt. Okay, if this will give you the in the electron volt, and this will give you the in term of the in term of angstrom one. Oh no, this will be in the nanometer one. Okay, when you put this value, and you will find out for the 20 kilo, this is for the kilo electron volt. If you substitute this value, and you will get this value, and this will be the lambda nanometer will be in the 1200 divided by the 20. So this will cancel, and this will give you the in the term of 62. So this will give you the 0 point. This is no this wavelength in the kilo, this is the in the volt, so there is 10 raised to power 3 here also. So this will give you the 62 10 raised to power minus 3. This is the nanometer, so this is giving you 0.002 nanometer, or if I convert into the angstrom, this will be 0.62 angstrom. So the corresponding SWL will be the 0.62 angstrom. So B will be the correct answer for this one. Check what's the calculation here. I don't think once, but I think this is this lambda. I'm just denoting this. The lambda SWL will be the 1240 voltage. This is voltage in the volt here. Electron volt we have already calculated, and this will come out in the term of the nanometer. Once you substitute this value and you will find out this wavelength will be the just 0.62 angstrom one. Okay, so this question is all about the question number 17. Let's move to the question number 18, and that is we have the last question of this assignment. So which of the following statement is and are true about the characteristic K radiation peak that we have already we know the system over intensity versus wavelength, and for the particular voltage we are having this one. If I increase the voltage, then it will become here. For increasing, this is giving this, and for the higher one, this is going this. This is the sharp peak. Notice this of this kind. This is the sharp one. This is of this and this one. Okay, something not this is not zero, but this is of something here. Okay, it is also something. So your this K radiation, characteristic K radiation, but when we will get the K radiation, why we are having this K alpha and the K beta? So the region we already know, discussed these things. The region when you if you in the statement is asked, it is appear when an electron of any cell get excited and move toward the higher energy state from a lower energy, and simultaneously the vacancy is filled by an electron of the higher state. No, this is not about the K radiation, because the K radiation is the one of the type of the X-rays radiation that we are getting, and it's open when it appear when a electron of the K cell get excited. Yes, because it is a K alpha or beta. This is K. The electron of the K alpha and get excited and move toward the higher energy state from a lower energy state. Yes, move toward the higher energy state to a lower energy, because we have the different where your electron move assignment is the vacancies, because as once this electron will remove simultaneously, this electron will move to the from the higher energy state to the this lower energy state. Simultaneously vacancy is filled by the an electron of the next energy level from this or this here. This once it is removed from here, the vacancy is filled by the next energy side. So this is true, the correct statement of for the characteristic K radiation alpha. So in the this C part, it is as it appear at the higher tube voltage. Is it appearing that the higher tube voltage? Yes, it is correct. This characteristic radiation are because at the lower voltage we are only having the continuous spectrum. We are not having the characteristic. The characteristic will appear as we increase the voltage, because it is also this characteristic wavelength are also inversely proportional to wavelength okay. This once when we increase the voltage, the characteristic will come into the picture. And so this is appear at the higher tube voltage, it appear at the lower tube, and no, this is not the correct answer. So B and the C only the right answer. Okay, so B and C are this is all about the question number 8. Okay, question number 18, sorry. So this is the question number 18, and then if okay, these are the diffraction method that we generally use. This is the two circle diffractometer here, because my the crystal is for this is used for the polycrystalline material, where your this sample is also rotating with theta, but your counter, that is the diffractive with the detector will detect with the double speed of this one. This is the one of the method of for the powder diffraction method. Is basically when the X-ray that is coming from the generator, then when you put at the monochromator, and this monochromator, this is the only the one single wavelength. This is the my crystal, that is monochromator is convert to the into the one monochromator. This is the K alpha, basically that you are the monochromator that convert into the single wavelength, and it this will incident on the crystal, and the crystal that is being rotated into a different direction. We have the different direction it is coming, because it keep rotating, and we for the different direction theta we get the the this diffraction pattern at the 2 theta degree, and when we rotate this theta will get changing, and the also this your two diffracted angle also gets keep changing, and we get the diffraction pattern corresponding to this angle of the incident. So this is the for the powder diffraction one. So this is all about the assignment number seven. In the first, we have discussed about the three type of the this side group arrangement, and they have named as the atactics and the isotactic and the syndotactics. And the later we have discussed about the X-ray in the how the X-ray are the in if you see in the question number 5, then later we also in the question number 5 we have discussed about the thermostat and the thermoplastic one. Okay, so we have also distinguished that the thermoset are the irreversible and thermoplastic are the reversible. In the sixth onward we have, or yes, seventh onward we have discussed about the XRD. 16 we have about the elastomer. So which one is the great elastomer? So basically elastomer are basically that deform when stressed and reform return to its original position when the stress is removed. If I remove this stress one, so it will remain, it's come to the its original one. So basically this is the reversible process, how reversible it is, or in turn of if I'm saying the reaction term in the, how reversible it, how it comes to, how I mean how it return to the original state, that define your how much elastic it is, and that's why your term is the elastomer one. Okay, so this is all about question number 6. 7, we how the in which range my X-rays are having. In the 6th, how your K alpha, L alpha radiation are named and the defined one, and the what are the difference between in the 9 we have discussed what is the difference between the lead diffraction method and the rotating crystal method. Lead diffraction method is basically where your we use the set of the range of the wavelength, but in the rotating crystal method we use the crystal where my wavelength is the not the range one, it is only the monochromatic wavelength, but my crystal is rotating there, and we get the different diffraction pattern with the different at the different angle and the diffract plane one also. So if this is in question number and then we have discussed how we can choose the nickel or the other material as a filter material for the different radiation. If we have the, if somebody, if let's say if a crystal having the different characteristic, the different camera, but we need only the one peak. So how we filter out? So the energy should be such that it absorbs the other, and we will remain with the only one. So energy should be such that I mean that should be lying between them, so that it can absorb the lower wavelength energy, lower wavelength radiation, and we will remain only with the higher one. So filter. This is how the filtration or the monochromator work. And so next one is the what is the difference between the diffraction scattering and the reflective one. So reflection is basically at the same angle that will be reflected at the same angle of incident one. The scattering is your random phenomena that splits in the all the direction. In 12th we have discussed the what will be the if interplanar spacing is that is given, so how this interplanar is I mean is interplanar will decide your wavelength of the radiation one, whatever the this the order of the this interplanar spacing and the wavelength of radiation will should be same, so that we can gather the diffraction pattern one. In question number 13 we have discussed the Bragg's law, that is your 2d sine theta is equals to and lambda. 15, what is your SW? SW is your short wavelength limit, and how this is changing with your voltages, and how their this mean intensity is changing with your with the wavelength and with increasing voltage, that we have discussed in the these three questions 14, 15 and the 16. I guess in 17, how you calculate the SW for the particular voltage. If the particular voltage is given, then how you will define the SW limit. In the question number 18, what are the true statement about the characteristic of the S radiation peak, how we will get the S radiation peak. And this, as I already told you, this is depend how from which energy levels state to it is coming to which energy level. So if it is coming to K, then it will be the K radiation, and if it is coming to L, then it will be the L radiation, and if it is coming to M, then it will be the M radiation. Then the in K itself we have the different radiation, that is the K alpha, K beta, and the K gamma. Alpha will be the when we are this the electron is the radiation that is when the electron is moving to the next to K level, that is the L1, or if we say the L cell, then will be the your K. If it is coming from the M cell, then will be the K beta, and if it is coming to N, then it will be the K gamma, and subsequently same as like the N. But if I talk about the L cell, if the electron is here, because this is my, let's say this is KLM, and this is your N. And so if now my electron is coming here, my vacancy is created here, so my electron is coming from here to here, then it will be the L alpha. And if my electron is coming from here to here, then the radiation that will be emitted, that will be the L beta, and similarly the L gamma, and the so on. So this is the way, this is how your radiation, how they are defined and they are named, and how they related with the energy and the characteristic pico. So this is all about the question number, no, the question all about the question number 18, as well as the assignment number 7. Then we will remain with the assignment number 8 only, that we will discuss in the next coming Tuesday, the same timing, at the same timing one. Okay, so let's wrap up this one, and this is all about. If somebody has any doubt in the any question, uh, let me know about the doubt, so that I can discuss. So 1 2 3 3. So if you have any doubt, so please let me know. Does anyone have any doubt? Okay, there is one question, I guess. So Isaac has asked, so can we do the vulcanization with fluorine? No, vulcanization is a process that we define, that the vulcanization is basically when we do the cross linking with the sulfur atom. So we can't do with the fluorine, and this is the process we define with the sulfur one. We generally do with the sulfur one, the vulcanization. This is how your this natural rubber convert to the elastomer and the ebonite, or the hard rubber that has the hard and the breathable. So this vulcanization can we do with the sulfur one. Okay. Any other doubt if you have? If you hand down, okay, no, okay. Any other thoughts on hands? No, thank you. Then let's then we will finish this meeting, and we'll and discuss the next assignment in the coming week, and we will discuss that when I will upload the following this lecture and the tube. On the YouTube and the drive as well, so that if you have any doubt, just mail me, or either ask in the this form also. Okay, thank you.